Hello everyone, and welcome back to the series on differential equations. Today we're going to be exploring a very useful method that is used to both approximate and solve differential equations, both of first order and also higher order differential equations, and sometimes is used to establish I guess you could say closed form representations for functions that wouldn't otherwise have a nice representation in terms of your common functions like sine, cosine, e to the x, and polynomials. So one thing that motivates this study of power series solutions is something that we discussed last time, which was Pickard's iteration method. So the Pickard-Lindelof theorem says that, okay, if we have this differential equation y prime is equal to fxy, with the initial condition that yx0 is equal to y0, f continuous in x and Lipschitz continuous in y, then there exists a unique solution associated to this initial value problem. And we can use the Pickard's iteration method to converge that solution yp. That is based on that existence and uniqueness theorem, with the initial iteration set to be equal to the value y0 and phi k plus 1 that sort of builds on top of that original function by typically adding terms in terms in terms. And the example that we looked at was a very simple equation, in particular y prime minus xy is equal to x with some initial condition, and we found that the particular solution, which most people should be able to find by now, is just equal to e to the x squared divided by 2x minus 1. But the Pickard iteration method doesn't give this to us. We have to algebraically build this closed form representation from that series function, because the Pickard iteration method was only able to give us something that sort of looked like 3 plus 2x squared plus 1 half x to the power 4 plus 1/12 x to the power 6 plus infinitely many other terms. And you're like, okay, if I cannot find a closed form representation, I'm just going to define this series as my solution, yp. Right? So generally speaking, the Pickard iteration method, phi k, provided that it does converge in the first place, is always going to converge to a unique solution yp that can always be expressed in the form the sum from k is equal to 0 to infinity of some constant sequence ak times x minus c to the power of k. Now, if you look at this particular representation, you see that this is an even function, which hints at the result that it's centered around x is equal to 0, but that's not always the case. Sometimes when you center it around other numbers, sometimes the patterns are a little bit more easier to see. So it's not necessarily that this is a Maclaurin series, so typically we take the particular solution to be a power series centered around some x value c, which need not be equal to 0, but sometimes is defaulted to be equal to 0. But when you're assuming that the solution can be represented in this form, you have to make sure that the issues of the solution doesn't occur after the center of the series for which you're trying to use to approximate it. For example, if we have the differential equation x minus 1 times y prime plus x times y is equal to the sine of x, notice that in this particular expression, x cannot be equal to positive 1. Therefore, if we say that the particular solution is of the form the sum from k is equal to 0 to infinity of a to the k times x to the k, this doesn't work because this is centered around 0, and this issue occurs at x is equal to 1. And if our initial condition is at 0 and we have to solve for it, we're going to have an issue that we can't bypass. Therefore, this has to be centered at, for example, 2 or somewhere arbitrarily close to 1 but on the right hand side of it. Therefore, one particular representation for the solution that would be reasonable is saying, okay, let's assume that it's of the form the sum from k is equal to 0 to infinity of ak times x minus 2 to the power of k. And then you can use this representation and then figure out, okay, well, what is ak in this particular representation? And this is going to be sort of the focus of what this video is about, right? So with this representation, we can obviously see a very interesting thing. At least from the Picard's iteration method, power series appear to be natural representations of ordinary differential equation solutions. So in some sense, if you're hoping that the solution looks like sine x, cosine x, polynomials or something, you're sort of wishing sort of a dream for differential equation solutions. But at least from this approach, we see at least power series are actually a more natural, beautiful way of representing ordinary differential equation solutions, and hopefully that power series has a nice little pattern. Right, let's look at a particular differential equation that you might be able to solve now, but it looks easy on the surface. In particular, xy prime is equal to the sine of x with the initial condition that y is 0 is equal to alpha, where alpha is just some real number. Right? So we can clearly see that this is a separable differential equation, in particular dy divided by dx is equal to sine x over x. And keep in mind, when x is equal to 0, sine x over x is arbitrarily close to 1. So if we define sine 0 divided by 0 to be equal to 1, which is equivalent to just defining the complementary sine function or the sinc function to be x, then we have this particular expression to solve, right? So how can you solve this differential equation? So we would obviously integrate both sides with respect to x. So you're going to be like, okay, y is equal to some constant c plus the integral of the sine x function with respect to x. Right? And you're like, well, I don't know the antiderivative of sine x over x, and you probably shouldn't unless you know a special name for it, because that's what we call a non-elementary primitive, i.e. there is no way to represent that in terms of the other baby functions that we know. And we sometimes abbreviate that function as just the capital SIX of that particular expression. If you know anything about this special function SI, you should know that SI of 0 is equal to 0. So you can find with SI of 0 is equal to 0 that that arbitrary constant will be equal to the alpha constant that it's initially set to, and hence the particular solution will be equal to alpha plus the sine integral function with respect to x. So that would be your solution if you had already given a name to this function. But if you don't have a name, you probably wouldn't be too happy with this representation for the solution. At least most people would not. So you're like, okay, well, how can I solve this? Because I can't use integration, but it happens to be a separable differential equation. This is where power series representations sort of have their light, because usually we don't seek a closed form representation of that power series. In this case, its closed form representation would be psi. But if you don't know psi, then you don't have a closed form representation. But with power series, we don't expect an existence of one. So power series is always a safe way to go, especially if your differential equation is a linear one. So now that we have some idea of what we're going to be going for, expecting, and also not expecting from these solutions, let's jump right into an example of how to solve differential equations with power series. So let's consider this particular differential equation, y prime plus xy is equal to x squared. It's first order, it's linear, it's inhomogeneous, you can use integrating factors to potentially solve it, and I invite you to maybe even try for this particular problem. But you're going to encounter an issue where you have the antiderivative of some function for which the antiderivative probably might not be obvious to you. Now, I will show you how to get what is accepted to be the closed form representation for this differential equation. But let's assume that you don't know actually how to solve it. Maybe you want to sort of convince yourself, maybe I don't know how to integrate this function, so what do? We need a nice representation for this. So this is where sort of power series has its light. Right, so let's assume that y has a power series representation. So let's assume that y looks like a0 plus a1x plus a2x squared plus a3x cubed plus a4x4 and so on. And it's very important to note that this is a power series centered around x is equal to 0, and make sure that 0 is not an issue with your differential equation. In this case, it doesn't have any big issues, at least. All right, so y is differentiable. Let's assume it's infinitely differentiable, i.e. this Taylor series does exist. So what does y prime look like in this expression? So what we're aiming to do is, okay, let's assume that this is our solution. What is a0, a1, a2, a3, a4 all equal to? Maybe there's a pattern, maybe there's not. We're not hoping that there is, but we would like it ideally. So the derivative of this expression is just going to be equal to a1 plus 2a2x plus 3a3x squared plus 4a4x3. The next term would be 5a5 x4. And obviously we have infinitely many terms down here. So on the left-hand side of this differential equation, it's plus xy. So what we're going to do is we're going to plus xy to this expression. And then we're going to sort of see what we get at the end, right? So when we multiply by xy, so what is xy equal to? So x times y is x times this original differential equation or series expression. So that's going to be a0x plus a1x squared plus a2x cubed plus a3x4 plus a4x5 and so on. And now we're going to add these two expressions together, and we're going to group them by like terms as well. So that'll give us the left-hand side of our differential equation because we know y prime plus xy is equal to x squared. And then once we have our series representation of the left-hand side, we're going to set that series representation equal to x squared, and then we're going to be able to get our coefficients from that. So what do we have here? So this is the only constant term that I have in my expression. So I have a1 plus, and then let's look for our linear term. So we have this term and that term for our linear term. So it's going to be 2a2 plus a0x. Let's look for our quadratic terms. So here's our quadratic and our quadratic. So plus 3a3 plus a1 x squared. If you can find a pattern quickly for this, that's obviously ideal, and you probably should. So 4a4 plus a2x cubed. Let's just list out a couple more terms just for practice. So that's going to be equal to 5a5 plus a3x4 plus 6a6 plus a4x5 plus and so on. In case you don't see the pattern, whatever power we have, plus 1 minus 1, the coefficient of the plus 1 term added together, that's that general expression. So if we go, for example, up to an, right, so plus all the way down to, we're going to have m plus 1 times a, m plus 1 plus a n minus 1 times x to the power of n. So that's the general nth term of that expression. All right, and all of this is equal to x squared, right? So notice that the left-hand side of this equation has a constant, a linear, a quadratic, a cubic, a quartic, a quintic, and a general term, but the right-hand side just has x squared, right? So therefore, this coefficient and the coefficient in front of x squared, which in this case is 1, must be equal to each other, and all of these other coefficients on the left-hand side, for example, this one, that one, that one, that one, that one, except for the x squared term, are all equal to 0. Right? So if that is the case, then we have that a1 is going to be equal to 0. 2a2 plus a0 is going to be equal to 0. We're going to have that 3a3 plus a1, that's the only special one, that's going to be equal to 1. And 4a4 plus a2 will be equal to 0. 5a5 plus a3 will be equal to 0. And all other terms are going to be equal to 0, except for the quadratic term because we have 1x squared on the right-hand side of our differential equation. Okay, so we have that a1 is equal to 0, but we don't know what a0 is, and that's unfortunate because we need to solve the next equation for a2, but it requires us to know what a0 is. So remember that y is equal to a0 plus a1x plus a2x squared, and so on. And our initial condition was that y0 was equal to 1. So when x is equal to 0, notice that all these terms are just going to go away. So on the left-hand side, we have 1 is equal to a0, and that's going to give us our a1. So use your initial condition to get any constants if it is possible, especially that a0 term, if you can at least, right? So we know what a0 is, and we know what a1 is, right? So a0 is equal to 1. a1 came out to, what was a1? a1 was equal to 0. And from here, what do we know? We know that a0 plus 2a2 will be equal to 0, which means that 1 plus 2a2 will be equal to 0, which means that a2 will be equal to negative 1/2, right? So that's our a2. Let's go to our next sequence. So we know that a1 plus 3a3 will be equal to 1. Keep in mind, this is the only special one. All the others are going to be set equal to 0 because this is our quadratic term, right? So that's going to give us, so a1 is 0 plus 3a3 is equal to 1. So a3 is equal to positive 1/3. Let's go to our next term, which is going to be our x cubed term, which is going to be a2 plus 4a4 is equal to 0. So a2 was negative 1/2, and then we're going to have 4a4 is equal to 0. So that means a4 is going to be equal to negative, that's going to be positive 1/8. Let's go to our x4 term. So we're going to have a3 plus 5a5 is equal to 0, which means that, okay, well, a3 was equal to positive 1/3. Then we're going to have 5a5 is equal to 0. And then we're going to have a5 is equal to negative 1/15. And again, if you seek a closed form representation, the goal is to find a beautiful pattern with these numbers, right? Which, at least to me, is not so obvious. Right, but one thing to notice here is that we have two positive terms there. Maybe that's the start of a pattern. We have a 0 here, and that's obviously going to throw off a lot of issues. But maybe we can add and subtract a term there and force that to be negative. And maybe we can force, two negatives to be there. Maybe we have two negatives in the next term. And then you can say, okay, well, maybe this power series, y is equal to, say, I don't know, some negative number, and then positive, positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative, and so on. Maybe that's the pattern that's going on here. We don't know, right? But anyway, at least we have the first few coefficients of these series, so that at least gives us some representation for our analytical solution, which sometimes is good enough. So let's just state what we have so far. So yp is going to be equal to 1 minus, well, we don't have a x term, but I'm just going to put it here anyway. So 0x, and then we have minus 1/2 x squared, plus 1/3 x cubed, plus 1/8 x to the 4th, minus 1/15 x to the 5th, and then you can find that the next term is going to be 1/48 x to the 6th, and then plus, and so on. Right? So any patterns here? Maybe. We have two pluses, we have two minuses, maybe the next are two pluses, next are two minuses. But this is a little problematic. So what we can do is we can try and force this pattern, try to build two negatives inside of this and make it like negative x or something like that, negative 1/3 x, I don't know. So if we do that, so this expression right here, just as a note, probably would be good enough in some sense for most people. But maybe you're trying to build a nice expression for this. So if you are, we can continue, and we can write this as, for example, 1 minus x minus 1/2 x squared plus 1/3 x cubed plus 1/8 x to the 4th minus 1 over 15 x to the 5 minus 1 over 48 x to the 6 plus and so on. But now what I'm going to do, since I did a minus x, I need to put a plus x at the end to balance that off, right? So now we have at least some sort of series, and there might be some pattern hiding in this, I don't know. But since we don't know what this function is, let's give it a name, right? And don't expect it to be elementary because it's not necessarily and rarely ever is. So let's actually give this solution a name. Let's call this function fancy e of x, and then we have that plus x term on the left-hand side. Right? So that is our particular solution where this fancy e function is approximated by this particular power series. Right? So the question is, okay, well, that's my newly created function. Is it possible that this actually does represent a function that I should know? That's the interesting question, right? Because as already mentioned before, the original equation was y prime plus xy is equal to x squared, which is a very nice equation, at least on the surface. It's the first order linear ordinary differential equation. So we can use integrating factors. So the integration factor in this case would be e to the integral of the function in front of y, which is x dx, which is just going to be equal to e to the 1/2 x squared, which at least on the surface appears to be very friendly looking. So therefore, our differential equation turns into the derivative of y times e to the 1/2 e to the 1/2 x squared is equal to x squared times e to the 1/2 x squared. And then we would, since this is a separable differential equation, then we have just y e to the 1/2 x squared, and that's going to be equal to some constant c plus the antiderivative of the function x squared times e to the 1/2 x squared dx. And this is where a lot of people would sort of be stuck at, I guess you could say, especially if you don't know any clever methods or special functions. So how to do this, right? So if you watched any of my integral calculus series, we actually introduced functions that can represent it. So if you're interested in sort of exploring how to take the antiderivative of this function, that's what I'm going to do in the next couple of minutes. So the first thing that you probably would think about, maybe I can use substitution, maybe I can use integration by parts, maybe I can use some trig substitution or something like that. All of them are perfectly fair. So what I want to do is I want to actually just call this mystery integral star for a moment. And this is just going to be the integral of x squared times e to the 1/2 x squared dx. So if you try just use substitution like u is equal to x squared or u is equal to 1/2 x squared, you're not going to get anywhere with that. If you use integration by parts, either letting u be equal to x squared, you're still going to have to integrate e to the 1/2 x squared, which you're going to be stuck there. And if you let u be equal to the exponential, x squared is going to integrate up into x cubed, which is going to make things even more complicated. So what I want to do is I want to force this into a u substitution form by decomposing my x squared. Because if you want to use a u substitution, you'd probably use u to be equal to that 1/2 x squared. But that only works if this leading function is a linear function. So what I want to do is I want to force a linear function to be there. So I'm going to write this as the integral of x times x e to the 1/2 x squared dx, and then I'm going to deal with that via u substitution, right? And you'll sort of see where this goes in just a moment, right? So if I let u, actually I'm going to use integration by parts. I think integration by parts is a lot more nicer for this, right? So let's do integration by parts, where this is going to be my dv and that's going to be my u. So let u be equal to x, so du is going to be equal to 1 times dx, and then dv is going to be equal to the rest of that, e to the 1/2 x squared dx, and then integrating that, that's going to give you your u substitution, which is just going to be e to the 1/2 x squared, and you could show that that is indeed the case. So once I have that, then integration by parts says that my integral is equal to uv, why's my e sort of embedded there? uv minus the integral of v du. Okay, so now we have this particular integral. It's a little bit more friendlier looking, but we still have to deal with this ugly little thing here. So what we're going to do is we're going to get rid of that 1/2 exponent. So what we're going to do is just let x be equal to the square root of 2u. That's going to delete that. So we're just going to have dx is equal to the square root of 2 du. And also from this we have that u is equal to x divided by the square root of 2. So once I transform this integral, I'm going to have x e to the 1/2 x squared. I'll leave that leading term alone. And over here we're going to have minus square root of 2 times the integral of e to the u squared du. So this e to the u squared should look familiar to you special function people as just the imaginary error function, which means we have to introduce that that normalization constant that you might recognize from basic probability theory. So this is just going to be x e to the 1/2 x squared minus square root of 2, and then I'm going to multiply by the square root of pi over 2. So square root of pi over 2 and 2 over square root of pi, and then e to the u squared du. And then that'll allow me to switch directly into error function mode, right? So this is going to be equal to x e to the 1/2 x squared minus, and then we're going to have the square root of 2 times the square root of pi over 2, which is the same as the square root of pi over 2, all under the radical, but I'll switch that in a moment. But this is just the ERFI function of u, right? Similar to the sine x, sine u over u is psi of u. This 2 over square root of pi e to the u squared is this particular function. And if that u squared changes to a minus u squared, you don't need the I in that particular expression, which we can talk about in another time in case you don't already know that expression. So what do we have? That means that wonderful little function star is equal to x e to the 1/2 x squared minus the square root of pi all over 2. And then ERFI, once we switch back, is just going to be x over the square root of 2. Okay, so that is our antiderivative that we couldn't do before. Okay, so let's switch back to the original problem, and keep in mind our original problem was e to the 1/2 x squared times y. The derivative of that is equal to x squared e to the x squared. And now we have a representation for that. So multiplying both sides by e to the minus 1/2 x squared, once we find that interesting representation, we're going to have our solution, at least in general form, to be equal to yc e to the minus 1/2 x squared, and then plus, so when we multiply both sides by e to the minus 1/2 x squared, this term will eliminate, and we'll still have that e to the minus 1/2 x squared in front of that ERFI function, right? So we're just going to be left with x minus the square root of pi over 2 e to the minus 1/2 x squared times the imaginary error function of x divided by the square root of 2. Now I have some common terms in terms of that e to the minus x squared, so I'm just going to group those terms together. But if you know anything about this ERFI function, if you take the ERFI of 0, you will get 0, allowing us to find that this constant actually is equal to 1 for our initial condition that we stated in our original problem. So once you have that 1, then we have that our y is equal to e to the 1/2 x squared of 1 minus the square root of pi over 2 times the imaginary error function of x divided by the square root of 2 plus x. Now, does this look familiar? It should, because from our power series method, we were able to find that our true solution was equal to 1 minus x minus 1/2 x squared plus 1/3 x cubed plus 1 over 8x to the power of 4. and then minus 1 over 15 x to the power of 5, minus 1 over 48 x to the power of 6, plus and so on, plus x, right? And this is that fancy function e that we derived, and this is another name for that, right? So if you don't know how to evaluate e to the minus 1 half x squared times 1 minus the square root of pi over 2 times Earphy of x over square root of 2 for various values of x, you can use this power series to approximate whatever its exact value is, right? But if you do not care about representing exact solutions in elementary or pseudo elementary fashion, then power series will give you practically the same exact thing. And all you have to do is just add more terms to get whatever level of accuracy that you desire for that particular solution for your differential equation. So the example that I used to illustrate power series methods was a first order linear differential equation. And you can of course solve higher order differential equations with power series, but we'll put that off until a later time when we actually start talking about higher order differential equations, because now we're sort of focused on first order. But natural question is, can we use power series for non-linear equations? The answer is yes, with the star next to it. There is some difficulties associated to using power series methods for nonlinear equations, especially if it's not a polynomial nonlinear term, like sine of y, the square root of y, stuff like that. So, to illustrate this method, let's use a very basic differential equation that you actually can solve with other methods. Y prime is equal to y squared with the initial condition that y0 is equal to 1. So this is a nonlinear equation. It's also separable, so let's actually go ahead and find the solution to this. So in particular, dy divided by y is equal to 1 dx, which means that minus 1 over y is going to be equal to x plus some arbitrary constant c. So when x is equal to 0, y is equal to 1. This is going to force our constant to be equal to negative 1, which means that minus 1 over y is equal to x minus 1, which means that 1 over y is equal to 1 minus x, which means that our particular solution yp is equal to 1 over 1 minus x. So that is our solution, no problem at all. But let's assume that you stumble across some issue where you can't integrate this, or it's not separable to begin with, it's not exact, it's not Bernoulli, it's not Riccati, it's just annoying to work with. Can we still use power series methods to at least get a power series representation for the solution? That's what we want, right? So at least we know what we're aiming for. So when we work through this, what we're actually doing, since we know the analytical representation, we're actually deriving the power series for this particular function, which actually serves another goal for this thing. That is, if you have a differential equation and you know the analytical solution, or you've named it, and then you solve it again using the power series method, since the solution is unique, that power series and that analytical solution represent each other, right? So it's a good way to generate power series for unknown functions or special functions. All right, so as usual, let us suppose that our solution has the power series representation of a0 plus a1x plus a2x squared plus a3x cubed, and so on. There's no x terms in this particular equation. We're not doing any fractions or scary things. So this is definitely going to be a Lipschitz continuous function in terms of y. So we're safe in that regard. So if it is in this form, that means the solution exists and is unique. Let's see if we can find some constants. So when y0 is equal to 1, this term is going to disappear. That's going to be equal to 1. So we have that a0 is going to be equal to 1. So we at least have the first constant. Now we need to figure out, okay, well, what is y squared going to be equal to? Now this is where it becomes very annoying for power series methods. So y squared is going to be equal to a0 plus a1x plus a2x squared and so on squared. Now, how do you square an infinite term polynomial? So that's actually quite annoying. Let's write out the first few terms. So let's do a0 plus a1x plus a2x squared plus a3x cubed. Let's go up to there. And that's multiplied by a0 plus a1x plus a2x squared plus a3x cubed, and so on. Right? And let's FOIL this in a very cautious way, and let's group by powers of x every time we do that. So we have a0 times a0. That is the only way you're going to have a constant term in this expansion. So we're going to have a0 times x to the power of 0. So we can move on to the linear term next. So we're going to have an a0 times a1x. So that's going to be one linear term. And then you're going to have a1x times a0. That's another linear term, and those are the only ways you can get linear terms out of this expansion. So that's going to be a0 times a1 plus a1 times a0 times x to the power of 1. Now, how can you get quadratic terms? So it's either quadratic times constant, constant times quadratic, or linear times linear. Any of those will be perfectly okay. So for example, we have this a0 times a2x squared, we have this a1x times a1x, and we have this a2x squared times a0. All of them are going to generate quadratic terms. So we're going to have a0 times a2 plus a1 times a1 plus a2 times a0 all times x2. And you can apply the same logic for x3, but there's actually a nice pattern that actually comes fairly quickly from this expansion. And you're going to have a0 a3 plus a1 a2 plus a2 a1 plus a3 a0 times x cubed. And if you notice that these constants, they're sort of permuting around each other in a similar way, the powers in the binomial expansion exponents sort of follow. Right? So once we have that, then we can write y squared as a0 squared plus 2a0a1 x plus 2a0a1 plus a1 squared times x squared plus 2a0a3 plus 2a1a2 x cubed. The next term is going to be equal to 2a0a4 plus 2a1a3 plus a2 times a2 squared, I guess you could say a2 squared times x4, and that will continue onwards. Now, let's find y prime. So y prime is going to be the same y prime as before. So that's going to be equal to a1 plus 2a2x plus 3a3a squared plus 4a4a cubed plus 5a5x4 plus, and that will continue onwards. And now we're going to equate y squared and y prime because that is our differential equation that we're trying to solve. So keep in mind, we already know that a0 is going to be equal to 1, so that's a good sign, a nice starting point. Notice that our constant terms are going to be equal to each other, so we have our first equation to solve, that a1 will be equal to a0 squared, and keep in mind a0 was equal to 1, so we're going to have that a1 is equal to 1 squared, which is also equal to 1. That's pretty nice. Now we're going to have that our linear term coefficients are going to be equal to each other. So we're going to have 2a0, a1 is going to be equal to 2a2, which we don't know. 2 on the left, 2 on the right, they cancel, so we're going to have a2 is equal to 1. That's nice. So we're getting a bunch of nice coefficients. Let's look at our x squared term. So we're going to have 2a0, a1 plus a1 squared. And that's going to be equal to 3a3, which we don't know. So we're going to have 2 plus 1 on the left-hand side, 3 on the right-hand side. So again, we have a3 is equal to 1. Huh, that's interesting. Let's look at the next term so we don't get ahead of ourselves. So we're going to have 2a0a3 plus 2a1a2 is going to be equal to 4 times a4. 2 plus 2 is 4, 4 on the right-hand side, so we have that a4 is equal to 1. So that's actually pretty interesting, and I actually invite you to use mathematical induction if you're on the theoretical side of math, and see if you can actually prove this next statement I will have, that ak is going to be equal to 1 for all k greater than or equal to 0. Right? So that's actually very nice. So what exactly does that mean? So that means our particular solution, if we don't know what it is going to be equal to 1 plus x squared plus x cubed plus x4 plus x5, and so on. Which means, as a power series, a closed form representation, we can write that as the sum from k is equal to 0 to infinity of x to the power of k. right? And that is our solution. But if you remember anything about this series, this doesn't always converge. It only converges for x belonging to the 0 minus 1 to 1, because this is what we call a geometric series, right? And if it converges, it always converges to the function 1 over 1 minus x, which is the same exact solution that we got using our separability approach. But keep in mind, we're like, okay, one solution is this, one solution is that, and by the Picard-Lindelof theorem, the solutions are unique, and therefore, the power series of 1 over 1 minus x is the sum from k is equal to 0 to infinity of x to the power of k. So can you use power series to solve nonlinear equations? Yes, but the algebra can be sometimes a little complicated. So just heads up on that. So I hope you enjoyed this video, and I'll see you in the next one. Take care.